Hello everyone. My name is Yongtaek, Professor of Department of Electrical and Computer Engineering at the Seoul National University. I would like to thank Professor Hyunyup Go, Professor Sang-Hoon Jeon, and Professor Arukian Nathan for giving me an opportunity to show the achievement of my group in stretchable hybrid electronics research today. This slide shows the content of my talk. After I briefly talk about wearable technology evolution, I will describe what the stretchable hybrid electronics is. Then I will talk about stretchable platform technology as a key enabling technology for the stretchable hybrid electronics. After I talk about stretchable printed electronics, I will summarize my talk. As we now may know, the wearable technology will evolve from accessory type to patchable and implantable types. Let's take a look at one movie clip. The title of this movie is Thrmoelectric 2012. The main character has patchable or implantable cell phone on his hand. I believe that stretchable hybrid electronics technology will make this touch device emerge in market in the near future.
I said this might happen. Look, find a piece of glass, put your hand to it. Do it, now. They really did a number on you, didn't they?
Who the hell are you?
You honestly don't remember any of it, do you?
No, I don't. Remember what? How do you know me?
The technology roadmap of body attachable patch, conformability, cost-effective large area manufacturing, performance, and environmental or biosafety are key factors to consider. For conformability, flexible versus stretchable platform technology can be used. As a near-term solution, flexible hybrid electronics is being used these days. Hybrid means any combination of conventional and a new device or process technologies. In order to further improve conformability as a midterm solution, stretchable hybrid electronics will play a key role. As you can see here, we can achieve a maximum level of conformability from the stretchable hybrid electronics technology. Finally, low cost and potentially disposable devices require stretchable printed electronics technology. Using stretchable hybrid electronics technology, we can implement a stably operating electronic system on a stretchable platform as shown here. In these areas, material innovation is very important. Stretchable electrodes, bonding, device protection, crossover, and via are key elements in SHI technology. In SHI technology, we need strain engineering for stretchable platform and the spring-like interconnect lines between rigid electronic components. Both technologies will protect the rigid components and the bonding area from failure caused by severe mechanical distortion. In order to engineer strain for stretchable platform, thickness modulation for the same materials, and modulus modulation using hybrid materials or chemical UV treatment methods are being used. It is very important to have a scaling up and easy fabrication features. In both approaches, handling of highly localized strain is a key issue for stably operating stretchable electronic system. Once we have stretchable platforms, we need to implement a spring-like stretchable interconnect between strain-engineered rigid areas. We need to consider fine patterning and high conductivity of the interconnect electrodes for highly integrated system. Novel materials show highly stretchable functions, but typically have difficulties in fine feature patterning and low conductivity. Structure-engineered conventional metals show high conductivity but limited feature in fine patterning and stretchability. Depending on requirements of various electronic systems, we need to carefully choose appropriate material and fabrication strategies. Our group spent several years developing printing-based strain engineering and printed stretchable electrodes with vertically buckling structure. In addition, we also developed printing-based device assembly technology. First, I will talk about printing-based strain-engineered platform and integration technologies. We embedded the printed rigid islands in elastomeric substrates in order to control strain distribution when the substrate undergoes mechanical deformation. On the rigid island area, electronic components such as LEDs or silicon ICs are placed, and the stretchable electrodes that are formed from pre-stretching and inkjet printing processes interconnect those components as shown in this figure. As shown in this slide, the printed rigid islands effectively suppress tensile strain applied to the components and protect them from electrical failure caused by the external mechanical deformation. In addition, pre-stretching and inkjet printing processes produce wrinkle structure with magnitude of ripples large to small from the printed rigid island. As I mentioned before, highly localized strain at the rigid and soft boundary is one of the major issues in stretchable hybrid electronics technology. This spontaneous formation of gradient wrinkle structure fully takes care of the highly localized strain at the boundary. These wrinkle structures can be easily pre-designed because the rigid islands are inkjet printed. Both regular lattice or customized pattern of the rigid islands can be engineered depending on the types of electronic patches you want to design. As you can see in this slide, body attachable LED displays can be easily implemented. Signal processing MCU chips can be also integrated on the same stretchable patch. Our technology was chosen for presentation in SID BW 2017 iZone, and we exhibited prototypes of attendees to experience cooking with finger in person in IEEE 2017 feature zone. The same effects can be obtained by using a pure epoxy bank printing process. When ICs have fine pitch contact pads, there is a high chance for short circuit formation between pads when silver epoxy is used for bonding. Therefore, we additionally print pure epoxy bank in between for short circuit protection, and its thickness promotes adhesion of ICs to the stretchable substrate. We found that elongated and pre-designed patterns of the pure epoxy banks provide the same effects as the rigid islands in terms of strain suppression, as shown in these slides. Therefore, when more complicated routing of numerous chips is required, the pure epoxy bank structure is very useful. We demonstrated remote soft robot controlling electronic skin patches. These figures show RX and TX electronic skin patches. One is mounted on the soft robot body, and the other is located on human skin. When specific control buttons are pushed, corresponding fingers of the soft robot can be operated. We also demonstrated stretchable vias and crossovers for multi-layered patches and matrix-type electrode formation. We believe that collection of such technologies will expedite transition from rigid PCBs to stretchable PCBs. Since display panels are rolled these days, if rollable PCB technology combined, truly rollable electronic system would be implemented. Using SHI technology, we recently demonstrated body-attachable thermoelectric battery technology. Using N and P-type rigid bismuth telluride legs, silver nanowire stretchable electrodes, and a soft heat-conducting structure, we developed a conformable thermoelectric array. In order to enhance heat conductance of PDMS substrate, we embedded magnetically aligned silver-coated nickel particles in the substrate. 220 NP pair showed much better performances than previously reported flexible and stretchable thermoelectric generators in terms of both Zeebeck voltage and power density. High conformability guarantees perfect contact on any complex curved surfaces. We successfully demonstrated the hot surface warning gloves, which shows hot signal when touched on hot surfaces of a kettle or a bottle containing hot water. My group has demonstrated several complex electronic systems that are mechanically stretchable and guarantee high performance of integrated chips. In comparison with printing sensors and integrating display and electronic directly on the stretchable substrate in the previous SHI approach, soft modular block assembly is so-called do-it-yourself wearable strategy. Like Google's DIY modular smartphone concept, prefabricated modular blocks of electrodes, sensors, displays, and ICs can be assembled like Lego blocks. Such a customized assembly of the soft modular electronic blocks enable us to fully customize how many functional sensors to be used, where to be placed, and how to be integrated with LEDs and silicon chips. One example is a tailored MP joint flexion monitoring system. Since people have their unique bone size and joint location depending on age, sex, or ethnicity, a ready-made body attachable device is difficult to be used universally. We integrated several modules directly on human hands for more accurate measurement of body movement. The next slide shows a movie clip which shows the procedure of the fabrication of a do-it-yourself wearable patch. This figure shows prefabricated modular blocks. For repeated usage of the fabricated patch device, medical-grade transparent adhesive film is first located on the hand. After checking the size and the location of MP joint, sensors are located on the right position and other blocks with the signal processing chip and the LED strain gauge are attached. Depending on the distance between various blocks, the stretchable electrodes are tailored with the scissors and placed. Finally, silver paste provides electrical contact and the coin battery is connected. When the power is on, the MCU sends the signal for initial calibration for maximum bending, and after that, depending on the bending angles, the strain gauge shows number of lit LEDs. Final topic is stretchable printed electronics technology, which I categorized as a long-term solution for conformable, low-cost, disposable wearable applications. Various stretchable electronic devices, such as light-emitting diodes and the thin-film transistors, have been reported in the literature. Although not all of them are printed devices, there are high chances for printing stretchable devices directly on the stretchable substrate. We typically expect that the performance and stability of devices will degrade under mechanical deformation. In many cases, stretchable devices use ultra-thin structure or wire-shaped materials, so the device performances are typically poor, but stretchability is excellent. Depending on the type of devices, some of them are already printed on the stretchable substrate as shown in green color, and others are either being under development or being considered very challenging, as shown in yellow and orange colors respectively. In all cases, one big challenge would be fine feature patterning of materials for system integration. This slide shows a pressure sensor and 20 dpi sensor array developed by my group. Hierarchical structure of silver nanowire electrode features high sensitivity. Pre-stretching and spray printing method was used for top electrode of the capacitive pressure sensor device. We upgraded the device structure by incorporating pressure sensing capacitor in gate insulator of CNT TFTs. Unlike capacitance signal reading in previous sensors, TFT transforms the capacitance change into current change under various pressing force levels. Therefore, it is very easy to integrate pressure sensing transistor into electronic patches. This video shows pressure sensing transistor senses pulses from neck and sends signal to pulse monitoring LED, which is blinking at each pulse. We also demonstrated pulse sensing even under folded arm conditions. Recently, we demonstrated with Atari, a technology for ultra-thin, wide pressure sensing levels, ultra-high sensitive resistive sensor with high linearity. Contact areas of the cellulose nanowire hybrid network change under pressure, resulting in such an ultra-thin performance sensor. Since the electrical contact varies the resistance value in local pressed area, we were able to make 1000 ppi resolution pressure sensing imager, which enabled us to produce fingerprint image and three-dimensional structure image. For now, in order to read out the pressure mapping signal, we need an optical device like a CCD, but we can also directly reroute the electrical mapping signals by using highly integrated silicon chip. In addition to pressure sensors, strain sensors can be also printed on a stretchable substrate. Since we are using printing technology as a major process equipment, any configuration of sensors and stretchable electrodes can be implemented. This result shows an example of using printed PSS bending sensors for finger joint and wrist movement monitoring. Pre-designed crack generation can much improve sensitivity and the linearity of the sensor responses. We can also use CNT as the sensing materials. This result shows an example of a finger joint rehabilitation monitoring system. We used the CNT material as a resistive bending sensor materials, and we also incorporated crack generation mechanism into the CNT-based strain sensor. As we exhibited the body attachable stretchable device at two major display conferences, the stretchable printed sensors were also demonstrated at iZone of SID-DW and the Future Zone of IMID. These videos show stretchable wearable UI/UX system based on bending and pressure sensors. Exhibition attendees actually wore the gloves and tried out the 3-axis sensing device. In addition, with a company named Mire Nanotech, we demonstrated force sensing touch film and the bending sensor-based flexible AM-OLED UI/UX interface. As you can see here, strain sensor array can be laminated on the back side of the flexible AM-OLED. If you increase the number of strain sensors in a matrix form, more UI scenarios can be implemented in the near future. Finally, I would like to share with you wearable technology roadmap again. As mentioned before, the wearable device will evolve from an accessory type via textile and patchable toward ultimate form of wearable technology implantable type. Since people want to imperceptibly wear smart electronic devices, more and more devices would be conformably contacted on human skin. This means that we definitely need a novel material set of substrate, electrode, insulator, semiconductors, which is completely safe with human body. In fact, such materials require process conditions totally different from that of conventional devices. Therefore, device platform and process technology need to evolve correspondingly. The device platforms of conventional electronics, even conventional silicon electronics, will evolve from rigid to stretchable. Correspondingly, there is no doubt on that new process technology such as printing will be used more in future. Eventually, future electronic devices would be extremely thin and light, would have maximum conformability, and thus the products based on these electronic devices would have full design freedom. My group have worked on printing-based sheet technology or stretchable PCB technology. This is a key enabling technology for electronic skin or body attachable patch devices to emerge in market as early as possible. Strain engineered platform, spring-like electrodes, stretchable vias, and the crossovers and the chip bonding onto stretchable substrates are main technical elements in sheet technology. I hope my group's work can contribute to the paradigm shift of the wearable technology and provides a better life for human beings through technical advancement in stretchable electronics and electronic skin areas. I would like to thank my students and the collaborators again. I would like to thank all of you for listening to my talk. I really want to see dreams that Hollywood movies predicted come true in the near future. Let's work together. Thank you.